Hi, everybody. Welcome to section 4.4, differentiating the natural exponential function. So in today's lesson, we're going to find a derivative of a natural exponential function. So here is a derivative of e to the x. So a function e to the x is differentiable, and what it is e to the x. So what does that mean? That means that the derivative of e to the x is itself. Okay, so the derivative of e to the x is just itself, e to the x. So let's go ahead and check out some examples applying this new derivative that we've learned. So find the derivative of the function g of x equals 3x to the negative 2 minus 4 e to the x. So the derivative of this would just be using regular derivative power rule with this first term. This would be negative 6x to the negative 3. And then we just saw that e to the x, the derivative of itself, the derivative of e to the x is just itself. And this 4 is just a coefficient. So this isn't being altered at all. It's just coming along with the e to the x. So it would just be the exact same thing. Minus 4 e to the x. And that would be the derivative. Okay, so let's go check out another example. So find the derivative of 3x to the fifth times e to the x. So in this situation, we have two functions multiplying each other. So here we would need the product rule. And recall that it's f g prime plus g f prime. So here we could pick your f and g. So f is 3x to the fifth. F prime is 15x to the fourth. G is e to the x, and g prime, well, what's the derivative of e to the x? Well, it is just itself again, e to the x. So if we put this all together in our derivative, we get 3x to the fifth times e to the x plus e to the x times 15x to the fourth. And just go ahead and simplify this. We get 3x to the fifth e to the x plus 15x to the fourth e to the x. So to clean this up a bit, we can factor out a common term. And a common term that these all have is a 3x to the fourth and an e to the x. So what I would be left with is x plus 5. And that would be my derivative. So this is also correct. I just want to clean it up a little bit and factor a common things out. Okay, so that's a derivative of e to the x. But what if we have something not just x in that exponent? What if it's some type of different function? So a derivative, a chain rule for exponential functions would be a derivative of e to the gx would be itself times the derivative of whatever is in that exponent. So let's see a basic example to show exactly what this definition means. So what if I had e to the 2x and I wanted to find the derivative of this? Well, the derivative of this is going to be itself. So I would write e to the 2x, just another copy of itself, but I need to find the derivative of what that e is raised to. So I need to find the derivative of 2x. So this would be times 2. The derivative of 2x is 2. And so my derivative is e to the 2x. Okay, so that's how you would find the derivative of a chain rule for exponential functions. So let's go ahead and try out a few examples applying this new chain rule. So here's A through D. I want to cover B first just because it's similar to what we just did and it's a little easier. So the derivative of e to the 5x is just going to be e to the 5x itself times the derivative of that 5x. So this would be times 5. So this would be 5e to the 5x. Okay, so let's go ahead and try out A now. Similar concept. This time we just do not have a simple 5x here. We have more of a expression here with the x to the fourth, x squared. But it's along the same lines of application. So the derivative of e to the 5x to the fourth minus 2x squared is going to be the same exact thing, e to the 5x to the fourth minus 2x squared, same exact copy of it, but I just need to find the derivative of this inside now, or this exponent now. And what that would be is 20x cubed minus 4x. Okay, so then just to clean this up a bit, we could say 20x cubed minus 4x times e to the 5x to the fourth minus 2x squared. And that would be the answer. Okay, so similar concept. It's just another copy of itself times the derivative of that exponent. So let's go ahead and try out another example, part C, same exact idea. So y prime is just going to be the exact same thing, e to the 10x squared minus 5x, and then the derivative of that inside, of that exponent, excuse me, which would be the derivative of 10x squared minus 5x. So times 10x, excuse me, the derivative of it, which would be 20x minus 5. So we could rewrite this to clean it up. So 20x minus 5 times e to the 10x squared minus 5x. And that would be our answer. Okay, last example. So here we have two functions dividing each other and we want their derivative. So what does that mean we need to use? We need to use the quotient rule. Okay, so remember that the quotient rule is g f prime minus f g prime all over g squared. So let's go ahead and pick our f and g. So f is 5e to the x. So the derivative of 5e to the x, so 5 just comes along with it, comes along with the e to the x derivative, and derivative of e to the x is just itself, e to the x. And g is 7x squared minus 3x, and the derivative of that is just 14x minus 3. So let's go ahead and put this all together in the derivative. So we get y prime is g 7x squared minus 3x times f prime, which is just 5e to the x, minus f 5e to the x times g prime, which is 14x minus 3, all over g squared. So we would have 7x squared minus 3x squared. Okay, so only thing we could really, well, it would be okay to leave it like that. We could simplify a little more, but it's okay to leave like this for now. Okay, so that's a derivative with exponential and the quotient rule. So now Let's go ahead and look at an application problem to finish up this material. And so it says the producer of TEOS, a coating for silicon computer wafers, believes from an extensive study that the national consumption C of TEOS over the next T years is approximated by this function here. C of T equals 14.5 e to the negative 1.2 T plus 0.14 T squared, where it's between 0 and 8. So the study was prepared when T equals 0, so 0 years. Find the rate at which the national consumption of TEOS is changing with respect to time. So when you see the word rate, that means you need to find derivative. Okay, so what we need to do now is find the derivative of that function. So I have C of T equals 14.5 e to the negative 1.2 T plus 0.14 T squared. So I need to find the derivative of that. So what I would end up with is the same exact thing, 14.5 e to the negative 1.2 T times the derivative of that exponent, which would just be negative 1.2. And then plus the derivative of 0.14 T squared, that's just a regular power rule, which would be 0.28 T. Okay, so if we simplify this out, we would get the derivative to be negative 17.4 e to the negative 1.2 T plus 0.28 T. So that's my derivative. Okay. And that's just me multiplying 14.5 times negative 1.2. So that's my derivative. And now what I need to do is find the rate at 2 years, find the rate at 5 years. So what I need to do is plug in 2 and 5 into my derivative to get that rate. So for part A is 2 years. So I would have T equals 2. So C prime of 2 equals negative 17.4 e to the negative 1.2 times 2 plus 0.28 times 2. So here's where you can just plug it into your calculator or Desmos and get a answer. So what you would end up with, if you're doing it correctly, is negative 1.01849. And so what does this answer mean? This answer means that the rate of change is negative 1.018 units per year, 2 years after preparation. Okay, so that's it. That's our rate of change at 2 years. Let's go ahead and check out part B now. Part B is asking for 5 years. So that would be C prime of 5. So it would be negative 17.4 e to the negative 1.2 times 5 plus 0.28 times 5. And once again, if you plug this all in your Desmos or calculator, you would get 1.35686. And so what this means, I'm just going to copy and paste from our previous answer, that the rate of change is 1.357 Let me write that. Units per year, 5 years after preparation. So now it's growing after 5 years. So this is an example of us using a derivative and an exponential function to calculate an application problem. So the hard part is always finding the derivative. But if you understand that you can find the derivative by the question, meaning rate, finding derivative, and then plugging in your time values, you should end up with the correct answer. But that's it for this section about derivatives of exponential functions. I'll see you next time. Thank you. Bye.